Hello, group number 19. Our design project is with GraceFall Incorporated on designing a wearable fault detection and protection device. Our group member consists of Akesh, me, Andy, Hua, Matthew, Shenzar, and advisor Dr. Alon Guez, and our co-advisor is PhD candidate Zoe Wang. Every year, 1/3 of Americans over age of 65 experience a fall-related incident, and 60% of them goes to the ER. So roughly 20 of every 100 people goes to the ER every year. There are no accurate and efficient methods of fall detection currently on the market that people can purchase. Existing solution for a fall detection system utilize the accelerometer, which may lead to many false positives for a fall. Because of sudden movement someone can perform throughout the day, like sitting down or reacting to a sudden scare or to dropping something and trying to pick it up. Alpha fall detection system will incorporate electrophysiologram signals, which will work together with the accelerometer to determine if a person is also experience panic from the fall and then actually falling from our accelerometer data. Stakeholder for our project consists of GraceFall Incorporated, who filed the patent on the project and will be providing us with the resources needed to complete the project. CHOP, Children's Hospital of Philadelphia, will also be providing us with the test facility and gathering patients' data. Elderly, athletes, and children who are all consumers. Our future stakeholders are hearing aids and headphone companies because we're trying to take these EEG signals from around the ear and it'll be smart enough to incorporate into the technology into their existing products. Tripping and falling is a big problem that can result in costly injuries and chronic pain. These incidents can happen in a blink of an eye, and our mission is to develop a software solution using machine learning methods that will use live data from a user-worn EEG and accelerometer to reliably detect a trip or fall event and trigger a fall protection device. The hardware we use for our project is the EEG headset that you can see at the top, the amplifier unit which is worn around the user waist, and the data acquisition system that you can see at the bottom. So the way the system works is when the person gets on the machine, it will jerk forward really quickly to simulate a fall. So then the EEG signal will pick up that, oh, this person got scared when he got on the machine right away, and then it will follow with repeated jerks in the same motion, so the person can get used to the motion. And then randomly near the end of the experiment, it will jerk in the opposite direction, which will cause another panic in the EEG. The software we use for our project is a data acquisition application, which is the software we use right now to collect data. We also use MATLAB to sort the data, apply machine learning methods, and we also use EDF browser for a quick visual of our data. This includes filtering, annotating events on the data, and finally Git for version control for our codes. A peer study review is about EEG signal collecting from behind the ear for seizure detection. This paper converts these signals into the frequency domain, and they find the average power over period frequency. These average power value over the period are the feature vector in which they feed into the state vector machine. And the state vector machine will classify these features and identify if a person is having seizure or not. So in the end, you're able to tell if a person is having seizure or it's a false alarm.
Hi, this is Matthew Gumaban speaking, and I'll be speaking about our solution. Our overall solution is split up into two parts, a software portion and a hardware portion. While both are important for solving the overall problem, the main focus for our group is chosen to be progressing the software portion. Our software portion can be summed up in three parts. First, to detect falls, we need to understand what to look for, so we need data. Using volunteers and a custom-built testing rig, EEG and accelerometer data was collected corresponding to a person falling and opposite, standing still or otherwise not falling. Next, we process our data, extracting the important data features that could be used to classify it. In our case, processing our data included converting the data from the time domain to the frequency domain, chunking the data into time intervals, and calculating features such as average power and peak frequency for those intervals. Finally, once we had a data set to work with, we researched machine learning and pattern recognition to identify and evaluate the performance of relevant machine learning algorithms. Using MATLAB's classification learner toolbox, we were able to create trained models with our data set that could be used to make fall predictions on new data. And eventually, software could be written to use these models to detect falls as they happen using live sensor data. Now, as we mentioned before, hardware prototypes were decided to be out of the scope for our group, but the hardware portion is future work that can be picked up by successor groups or other researchers. It would essentially involve implementing the fall detection software into a user wearable sensor rig and actually developing the deployable airbag system that would cushion the fall. Now, here's a system workflow diagram of how our software solution would operate. The user is wearing an EEG and accelerometer sensor rig that sends data to an onboard data acquisition device. Here, the raw data goes through synchronization and preliminary processing and is sent to the onboard computer. In the onboard computer, our fall detection software is running and constantly analyzing the data to look for patterns corresponding to the user tripping and falling according to our trained machine learning models. In our device's case, the user must be accelerating downward and experiencing a panic or sudden distress. These are corresponding to the accelerometer and EEG readings. If both instances are occurring, the software will output a signal to activate the onboard protection systems, such as the airbags mentioned earlier. So, wrapping up our project, we should talk about what we accomplished and what work can still be done in the future. In terms of our accomplishments over the past 3 terms, we were able to develop a process for collecting and processing experimentally acquired sensor data and training machine learning models using MATLAB. We developed our overall conceptual system workflow of how the various software and hardware components will interact with each other to detect falls, and we were able to identify the relevant and highest performing machine learning algorithms that can be used to power live fall detection software. Now, with regard to future work for the project, these next couple points were originally activities planned for the spring term, but due to the COVID-19 pandemic, progress with these items were ceased out of safety concern for our group. So first, the accuracy of our predictions can be greatly increased with a larger and more varied training data set. So work in this respect could be recruiting more volunteers and collecting more fall data to feed into our MATLAB models to improve their accuracy. Next, we were also not able to complete the live data implementation of our software. Continuing this would include developing a software that can accept data streamed live from sensors and be able to continuously analyze incoming data in real time. Finally, as mentioned earlier, there are many opportunities for hardware work for this project. These include performing live testing with the sensor rig, like in optimizing sensor placement on the body, miniaturizing the sensor rig for user comfort and discrete appearance, and of course building and integrating the deployable airbag system that would actually mitigate the falls. Now, to talk a little bit about the potential society impacts of our project, to give a little perspective, the average cost of a typical hip replacement we found to be, without health insurance, around $40,000, which is a large chunk of change to have to incur for something that happens so quickly and so out of nowhere. So the goal of our proposed solution here is, first off, to improve the quality of life of our users and to provide them a layer of protection against hip or other bodily injury with as little interference to their everyday life as possible. And we'd like to provide them these life-saving measures, hopefully, or save them from these costly fall injuries and chronic pain that they can experience throughout their life as a result from these injuries.
A major part of the project was to acquire new data sets to train the algorithms of the system, as any research involving human subjects requires approval from the Institutional Review Board, IRB, which is an administrative body established to protect the rights and welfare of human research subjects. GraceFall operates under CHOP Children's Hospital of Philadelphia and has been approved by its IRB, which complies with the registration requirements for both Office of Human Research Protections and the Food and Drug Administration. Nobody from the senior project design team was involved directly with the testing of human subjects. The team only learned the testing equipment and procedures. All the testing was done and data was given to us by members of the GraceFall, who are included in the IRB. During the fall term, the focus of the project was to try different types of algorithms to compare their ability to distinguish between fall and non-fall events. In the project, a fall event was associated with a stutter that occurs during the shock and can be seen in the EEG data. Another goal during the first term of the year was to familiarize ourselves with the data and the hardware, and work on filtering and separating the EEG data. As a result, it was found that the utilization of linear algorithms for EEG data did not yield any results, so the focus shifted onto SVM and KNN algorithms. During the winter term, the team closely worked on the parsing new datasets and looking into performance of SVM and KNN algorithms. The accelerometer data were analyzed, and a simple threshold algorithm was created to help in distinguishing between fall and non-fall events. Also, the OpenBCI hardware that is used for the data capture was studied for the possibility of obtaining live data. The winter term resulted in the successful performance of the KNN algorithms, and that the OpenBCI amplifier can be connected to MATLAB using lab streaming layer of the liblsl MATLAB library. From the results of the winter term, it was decided to work on and improve EEG algorithm by bringing the accelerometer data into it as one of the features. The team also set to test the live data acquisition from the EEG sensor and the performance of the algorithm on the new set of data. So currently, the EEG algorithm utilizing cosine KNN method on preliminary testing resulted in 98% and 95% accuracy on non-fall and fall events respectively. Further testing is required to ensure accuracy of the algorithm.
A few necessary changes had to be made in the scope of our senior design project. In the spring quarter, we were going to test new trials on new data because our machine learning algorithms required much larger data because of the supervised nature. And due to the COVID-19 pandemic, these trials were canceled, so we had to work with the pre-existing data. The group had started live data acquisition research towards the end of winter quarter, and the continued effort on this wireless transfer between for the hardware portion could not be continued because many of the hardware is on campus and you need it to be handled in person, and as we know, campus closed, so we couldn't continue efforts on that. And as for our EEG implementation, we were able to get a successful implementation that relied and was only dependent on EEG signals. The next phase in the spring quarter was to replace one of the EEG features, which were in time domain, with an accelerometer-based feature, which focuses on the X, Y, and Z positional data. And that way, our algorithms could be embedded together with the pre-existing accelerometer implementations, and we can incorporate EEG as well, and that would improve reliability and efficiency. But we had to cancel this portion as well and stop where we left off with the EEG portion.
Now I'm going to demonstrate a method of training the dataset after the data have been extracted and filtered from the original EEG raw signals. This is the input data for the training machine. Using two different features here, we can generate a two-dimensional graph to better help the machine classify between the two classes that we have here, fall and non-fall. The first feature we have is the sum peak, which was extracted from the raw EEG signal after using various pre-processing methods, including noise filtering and other signal filtering and analysis. One of these data points is the sum of peak of a selected bin size. The second feature, peak power, is also extracted in a similar manner after converting the original signal to the frequency domain. And the third column, we have the two class, fall and non-fall. Now I will demonstrate how we classify the dataset using the built-in classification learner app in MATLAB. Using this, we can create a new session and input the data that I just showed. Our response class is based on two unique classes, which is fall and non-fall that I showed earlier, and the predictor is the sum of peak and the peak power. Everything else is kept as default, and we can start the session. On the plot on here, we can see that the input data of fall and non-fall, with non-fall being orange and fall being blue here. There are many fine-tuning settings that we can set to improve our machine learning. For example, you can set the misclassification clause here to weight the cost when it misclassify higher, and also setting distance for the model. For the purpose of this demonstration, I will keep everything by default. To train different model, I will select it from this menu here, and we will choose to train all of them. This is a small set of data, so it shouldn't take that long. After we finish training, the plot will show the misclassified data as axis on the graph here, and it will show each individual accuracy value in percentage. The best classifier that we found here was 95% accuracy, but with further tuning, we were able to achieve 96% accuracy in testing. After we train the model, we can export the model here. I have already exported the model ahead of time here, as you can see. And within the model structure, we can see the predicting function itself, the required variable to put in the function, and in here you can find other setting that the model has. For example, the distant metric it used was cosine. Going back to here, it also has a documentation of how to use the predicting model and the function to predict future data.
Our goal for the fall quarter is seen in this Gantt chart here. As mentioned before, the data filtering was to be explored on the EEG signals, and we explored different algorithms such as the linear methods like perceptron and SSE. And much of this quarter was learning about the pre-existing hardware solutions for reading EEG signals and accelerometer. And also we had to study a lot of research papers to learn about which algorithms we wanted to explore and really implement. Shown here is our winter quarter Gantt chart, and focus for this quarter was to narrow down our algorithms, which we decided to go with KNN and SVM algorithms specifically. Also finalize hardware components, and worked on accelerometer thresholding method. And lastly, towards the end of the quarter, we investigate live data acquisition using MATLAB and Bluetooth dongle. Shown here is the spring quarter Gantt chart, and many of the components were canceled due to the COVID-19 pandemic, but our goals were to integrate an accelerometer as a feature into the KNN algorithm, as mentioned, and we wanted to have a live working data acquisition tool in order to test it on live subjects, and that way we could get feedback from our possible stakeholders. Our group's different respective roles are shown on this slide here. Akesh, I'm the lead for the group, and I'm responsible for the logistics and interfacing between our advisors, Dr. Alan Gazenzo, and our stakeholders and sponsors such as Children's Hospital of Philadelphia and GraceFall Inc. I was also responsible for feature extraction and program optimization to make sure our program's running smoothly. Andy Wong, he's responsible for our testing and also was part of the data extraction and running different tests for gathering new data, and he helped with debugging. Was responsible for development of our classification learning and creating our supervised set used for training data sets. And he's also responsible for the graphical user interface, which was supposed to be part of the spring term, but unfortunately that was canceled. Matt is responsible for algorithm development and selecting which algorithms we're really focusing down on, and he's also part of the live data acquisition team with Sanzar, who's our hardware and circuit design person, and he has had a lot to do with accelerometer implementation, but that also had to come to a stop in the spring quarter. The team's out-of-pocket budget is shown on the slide here. The cost shown in blue, which tallies around $1,450, was covered by our sponsors GraceFall and Children's Hospital of Pennsylvania, so no additional funds had to be covered by the group. So the importance of conducting our senior design project is that currently in the market there's accelerometer based fall detection and not any really based on EEG, and this is a big problem because when one person like bends down too quickly or turns to the side, it leads to a lot of false alarms, and introducing the EEG really improves the reliability and accuracy to make sure that these systems are accurately detecting fall when they need to be, and it has the potential to prevent lifelong injuries which can cost thousands of dollars and possibly be fatal, and prevent and save people's lives. As for the results of our machine learning algorithms, of the 6 tested here, our best performing one was KNN, which is the cosine base at around 96%. And our worst one was the Bayes algorithm at 90.6%, which is not all too bad. Future work may be testing larger data sets, so these numbers could change. A lot of lessons were learned during the research, development, and testing phases of the senior design project. We learned that a lot of knowledge was required in order to really choose which algorithms we wanted to tackle, and we had to learn about how to implement these and read a lot of research papers on machine learning algorithms and how to data process. We dealt a lot with sensors and signal analysis with our EEG and accelerometer sensors, and really learned about like filtering these and getting rid of noise and really how to deal with signals. And the accelerometer was left alone because that's simple X, Y, and Z. It was also very important to divide the work among each of the group members, because that helped in prioritizing work and also ensuring that each person's responsible for different departments, and it really helped balance the project as a whole. So for the fall, winter, and spring quarter, we learned based on our different focus for each quarter. We learned a lot in the fall about data acquisition and algorithms through our research. In the winter, we learned a lot about the specific algorithms we decided to focus on, such as KNN and the EEG implementation. And in spring quarter, we were going to learn a lot about accelerometer, graphical user interface, and live data. Finally, I would like to discuss some challenges which we face. Some of the biggest challenges that recurred during the span of the project included a lack of large data. Specifically, the group didn't have test data on elderly subjects, who are the main stakeholders of the project. Additionally, we didn't have enough data to train some of our learning machines due to their supervised nature. It may be possible that algorithms are very accurate when fed larger amounts of data. The group made efforts to combat these issues by running additional experiments, but unfortunately, to ensure the safety of the members, the project has been terminated for the spring quarter due to the ongoing COVID-19 pandemic, and research has also stopped. So some future work and suggestions for some people who decide to maybe pick up the project in the future. Maybe explore neural networks and convolutional networks, which have shown to provide good results in literature of up to around 96%. The future groups should utilize accelerometer data as a feature and not just a threshold into the machine learning algorithms. The previous features were dependent on the amplitude response of EEG in the time domain and power in the frequency domain. Both of these are EEG dependent alone, so accelerometer positional data with the X, Y, and Z axis should be incorporated and replace the time domain feature. The group should pursue live data capture and processing of the algorithm as well, because devices that will have the embedded machine learning algorithms will need to be worn throughout everyday activity. And this is much more feasible if it was a wireless solution. I'd just like to say thanks everyone for the opportunity to partake in the senior design project. Thank you, Dr. Fontecchio, for all your hard work, and also our advisors, Dr. Alan Kez and Zoe Wan. And all the constructive feedback that we've received has helped a lot with Dr. Friedman as well. So thank you all.